Hello. In this session, we see Ampere's law. In electrostatics, we had two basic laws, Coulomb's law, and which is extended to Gauss law. The same way, magnetostatics, we have two fundamental laws, Bird-Savart law. From the Bird-Savart law, we extend to Ampere's law. In the Bird-Savart law, what we learn is, so through the current carrying conductor, if I current is flowing, so we consider here dl differential length. At the point P, we can measure magnetic field, differential magnetic field dH by the relations. So distance vector or the angle is alpha. So we can write it is dH is product of I dl ideal and a sine alpha. That means the angle between the line joining the point P to the dl. So alpha and inversely proportional to the square of the distance. And the proportionality factor is 4 pi. So that infinitely small current carrying conductor, which makes the differential magnetic field at point P is, we measured at dH. Now in this Ampere's circuit law, we go to find that magnetic field so from a current of loop. Let's see that what is Ampere's circuit law. So Ampere's circuit law states that the line integral of H around a closed path is the same as the net current I enclosed by the path. So we can write it is current enclosed is equal to closed integration, line integration over H to dl. Let's see. So I'm taking here the current carrying conductor I, through which current I is flowing. And here we are getting magnetic field. So we know that what is the direction of magnetic field if current is going upward directions. If current is in these directions, so magnetic field is in these directions. So which is one closed loop. So now we can write this as here H dot dl is equal to I enclosed. So here I is the current and H is a magnetic field. So we will learn P is equal to, there is a one relationship, B is equal to mu H. So based on this equation can be modified. So which is equal to here. So closed integration, line integration, B dot dl is equal to mu naught I, because we conduct this in a free space. So that H multiplied with the mu, which becomes mu naught. So here, let's explore this detailing. So by Ampere's circuit law, so current enclosed is, that is the current flowing the closed loop is I enclosed is equal to so H dot dl. H dot dl. So it is enclosed, so that you are taking closed integrations, line integrations. H dot dl. See H dot dl. So we can apply here Stokes theorems. So what is the Stokes theorem? Simply we can say is, if we have one closed line integrations, which can be converted to double integrations, that is surface integrations. So now I here have H dot dl, that is under closed line integrations. So we can write it is, so double integrations. Here it is converted to double integrations. H dot dl can be del cross H dot ds. So here closed line integration change it to surface integrations. And H dot dl, that is a dot product, is written as cross del cross H dot ds. Here dl is ds. H dot is del cross H. So that we can write it is. Already we know that what is the current is. So current enclosed is equal to, so current density J dot ds. So now we can write here. So I enclosed is equal to J dot ds. So yes, so that J dot ds is equal to del cross H. So now we can write, so del cross H is equal to J. So from Ampere's circuital law, we derive del cross H is equal to J, which is the third Maxwell's equations to be derived. So finally, we will we will collect all these results and we formulate, or we will write 4 Maxwell's equations. So this del cross H is equal to J is the Maxwell's third equations. So where we find application of Ampere's circuital law. So we can apply Ampere's circuital law to determine the magnetic field where symmetrical current distributions. See that in Gauss law we apply for symmetrical charge distributions. The same way Ampere's law we apply for symmetrical current distributions. For example, for finding magnetic field from infinite line current, infinite current sheet, and infinitely long coaxial transmission lines. For example, I'm taking infinite line current distributions. So see here, so I'm taking infinitely length of a conductor in the Z directions. In this Z directions, and we consider Amperian path, that is a magnetic field closed path, which is in horizontal plane here. So where we measure magnetic field is the point P is here, which is situated from the origin. The distance is rho distance. That is radial vector is rho. And if it is, the magnetic field can be tangential to this closed loop. That means, so magnetic field will be in this. So if it is in this, there will be only one component available in the net magnetic field. That is A pi. Because magnetic field is tangential in this to this loop. The two, it is in horizontal. So that A pi component is available in the net results. So we can write. So we can write current enclosed in this long infinitely current conductor. So I is equal to, so H pi A pi dot rho d pi A pi, which is equal to H pi dot 2 pi rho. Here rho is the radial distance. So we can find what is H pi, that is a magnetic field at the point P. So magnetic field is H pi is equal to I over 2 pi here. So this is the magnetic field over point P. The same way, we can find what is the magnetic field from the infinite sheet of current. For example, I'm taking a sheet here, which is infinite in size. So current flow is in these directions. So these are the current components. So current components are, that is current component is going y directions. So current is, sheet of current is in these y directions. We know that if a current is flowing in these directions, what will be the magnetic field? For example, we learned that if current is flowing in these directions, so magnetic field will be in these directions. The same way, if you tilt these current directions in these y directions, then magnetic field will be in this way, which forms one closed path, a closed loop. So here we have a closed loop. So here we have a closed loop like this. So I'm taking here 4 path. So 1 to 2 current directions, 2 to 3, and 3 to 4, and 4 to 1. That is, we have a 4 magnetic path. So which forms one closed loop like this, which form one closed loop. So in this rectangular path, so 1 to 2, which is the height is A, 2 to 3, the width is B, 3 to 4 is A, again 4 to 1 is B. If you notice this, 1, 2, 3, 4, both are same width but opposite in directions. And 2 to 3 and 4 to 1 are same width but opposite in directions. That means field is in opposite directions. So if you see finally what is the resultant magnetic field, so 1 to 2, 3 to 4 are equal and opposite, so they are cancelling each. And 1 to 2 to 3 and 1 to 4 equal but opposite in directions. So we can write the magnetic field finally, which is available only in the other directions. So current is flowing in the y directions. So as per Biot-Savart law and Ampere's, you know that if a current flow in these directions, there is no magnetic field in these directions. So current flow is y directions, so that there is no HY component. That means there is no magnetic field in y directions. So possibly magnetic field will be in 2 directions only. One is x directions, second is z directions. But due to this symmetrical, so current, that is a magnetic field in z direction is cancelling out each. That means 1 to 2, 3 to 4 equal and opposite. So they are cancelling each. So remaining only one direction is, that is x directions. Let's start up. Let's write this magnetic field component. So magnetic field is H naught, that is a positive magnetic field if Z is, that is above 0, that is greater than. So Z is a positive, so magnetic field is positive. And Z is negative, that is in these directions, so magnetic field will be negative in these directions. So we have 2 magnetic field components, that is in x directions. That is, now we can write what is the total magnetic field. So total magnetic field H is, that is a line integration, closed line integration over the path H dot dl is equal to, so 1 to 2, 2 to 3, 3 to 4, 4 to 1. In this, so 1 to 2 and 3 to 4 are both are equal and opposite, so they are cancelling each. So the resultant is only 2 to 3 and 4 to 1. So we got a total magnetic field is 2H naught B. That means here this electric magnetic field is 2H naught B is equal to KY, that is the current directions B. So that B cancel. So H naught is equal to, so KY divided by 2. So the total magnetic field is equal to KY over 2. So what the direction is? It is in x directions. So for a positive z value, it is 1 by 2 KY AX. For negative z values, it is minus 1 by 2 KY AX. So generally, we can write this. So here it is a y and x. So that in general form, we can write the current density is H is equal to 1 by 2 surface current, which is normal to the sheet AN. So this is the way we can measure magnetic field from the current sheet.